Okay, deadlock, in fact, we have talked about it before, okay? But today we're going to talk about it in a much more formal way. We need to describe what is deadlock, okay, in a professional way, the formal way that it is described in relation to operating systems. And we need to present some methods to deal with deadlock. So these methods include, as showing here, deadlock prevention, deadlock avoidance, and deadlock detection and recovery. Okay? These are the main topics with deadlock. Deadlock is not a situation that's only related to operating systems. It is a generic situation. The main cause of it is the way we coordinate the assignment of resources. So it's also related to the resource assignment problem, how you assign resources such that you don't have what we call deadlock in here. There are many fields in which you might have deadlock situations on roads, transportation systems, general type of networks, and in one of the problems that we have dealt with, which is the dining philosopher problem, I think you have seen the deadlock there when each one of the philosophers trying to eat and holding one chopstick. None of them will be eating. So it's a problem that we are aware of. We call that the system, we say that the system has a deadlock when none of the processes, or when there is a set of processes, none of them is progressing. None of them is progressing. Basically because of 4 conditions that are held, and in a while we will say what are these conditions. But when we see a number of processes not progressing at all, because they do depend on the resources held by other processes within the same set, then what we have is a deadlock situation. You might have multiple deadlock situations in a particular system, here in relation to operating systems. One situation of showing you a deadlock, okay, if you have like 2 semaphores, as showing in the example, okay, the second example, for example, look at it. Semaphore A and semaphore B, both of them initiated to 1, okay, and these are mutex semaphores, okay. In fact, they do represent a locking mechanism for resources, resource A and resource B. So if you have processes P0 and B1, and we had P0 to request resource A, and then we have some kind of context switching here, then P1 requesting resource B, because that's how the execution of P1. So now P0 holding resource A and P1 holding resource B. Any one of them cannot proceed because each one of them is requesting the resource that's held by the other. P0 wants resource B, currently held by P1, and P1 wants resource A that's currently held by P0. So if that's the execution code of these 2 processes, none of them will progress. None of them. Now, if I want to code something like that, in code to show deadlock, basically I just need to create what? 2 threads, and I create 2 semaphores, okay, or any locking mechanism in this case. So I just put it what? As a lock, okay, so you can have any type of lock, implementing mutex lock, which means we have only one instance of the first and second resources there. Then you run these 2 threads. What we want is that one thread will request a resource, the other supposed to request the opposite resource, okay, the other resource. So if thread A here requesting a resource first, okay, then the very first resource to be requested by thread B is resource second, okay? Then we want to implement the context switching, so we're going to have the sleeping time between the requests of the first resource and the second resource. So we have the first thread A requesting resource A, okay? And then after that, you're going to have some kind of what? Sleeping here. So you can have a sleep function here to make sure that there is a context switch. During that time, thread B will run and will request what? The second resource. So now we have the first resource with A and the second resource with B. And then any one of them running will be requesting the the remaining resource. None of them will manage to, because these resources are held by, okay, so we have first resource by A and second resource by B. So this is a deadlock situation that you can implement it in what? In code. And now to represent deadlock, okay, we can represent it in like we can have a particular representation of processes and resources, because we said this is very much related to resource assignment, okay, problem. So we have a number of limited resources in the system of certain types. And in many situations, we have a number of instances of the same resource, right? So we might have multiple hard disks. We might have multiple ports of the same type on the computer system. These are multiple instances of the same type. We are going to introduce RAG, being the resource allocation graph, in which we will show resources and their instances that are available in the system, as well as the processes who are running in the system. A process is represented by a circle, while a resource is presented by the square. Okay? So you see this is a representation of a process, this is a representation of a resource. If you see these small squares inside a resource, or sometimes basically dots, or even sometimes a number, it means the number of instances of this resource. So in this case, I have 4 instances of the resource showing under the circle at the top right of the slide. Okay? Now, these processes will be requesting resources from time to time. So in this case, I have PI, process PI, requesting resource RJ, requesting a resource of type RJ, and I have 4 instances of RJ. So the arrow is from the process to the resource. And when we have the arrow from the resource to the process, it means that an instant of this resource, RJ, is currently assigned to process PI. Okay? So if we have multiple of these processes and resources, the result is a resource allocation graph. So this is a directed graph, and the meaning of the arrows is explained in here. We have assignment, request, and we have what? Assignment. This is a request, and this is an assignment, okay? We also have a claim edge. A claim edge is a dotted request, and that means the process might request. The process might request a resource of a particular type. We also might have directed, or let me say, weighted directed graph, in which we have a number here on the top of the arrow. A number of the top of the arrow indicates the number of instances requested by a process, a number of instances of a particular resource type requested by a process. So if I have here 2, it means PI is requesting 2 instances of resource RJ. We will show examples of the resource allocation graph, but that's the terminology for it. Now I can say that a system has a deadlock situation, okay, if 4 conditions are held simultaneously, okay? 4 of them together, okay? And these conditions are mutual exclusion. It means only one process at a time can use a particular resource. The second one, hold and wait, where I have a process holding resources and requesting additional resources that it is waiting for, okay? So having resources and waiting for its request for additional resources to be granted, okay? So hold and wait. The third condition, no preemption. No preemption means the process voluntarily release resources, not by force. Voluntarily release resources that it is holding. And the fourth condition is circular wait. Circular wait, we said, in a deadlock situation, we have number of processes, they are waiting for each other. None of them can progress. We can express this in this format, having processes P0, 1, 2, and say M, So we have m processes, or n processes, sorry. Then P0 to Pn minus 1 are n processes. If we have P0 holding resources and waiting for resources that are held by the next process, say P1, okay, and P1 holding resources, as well as it is waiting for resources that are held by another process, say P2, and so on, until we reach towards the end where we find the last process, Pn minus 1, holding resources and waiting for resources that are held by P0. So the result is what? A cycle, right? We have a circle of waiting, P0, P1, P2, P3, okay, and then back to what? To P0. None of them will progress, okay? So this is a circular wait condition. 4 conditions together. If they are held, then we say what? We have a deadlock situation. If 3 of them held together and 1 is not, we don't have a deadlock, okay? They have 4 of them to be true. Now back to resource allocation graph. These are resource allocation graphs, examples of. And how would I read the resource allocation graph? Well, in fact, you can get to know lots of information from resource allocation graph. For example, you can know the number of instances of a particular resource. I can say I have 3 instances of R4. You can know the type of resources. I have 4 types of resources, R1, R2, R3, R4. I have 3 processes, right? I have P1 requesting resource of R1, while currently it is assigned an R2 resource. Okay, so we can read it that way. Now, how this will aid us deciding whether the system has a deadlock situation or not? The rule is like this. If the resource allocation graph is of a single instance means all resources are of single instance. We don't have a resource type that has multiple instances. Then in that case, if you manage to find a cycle in the graph, it means we have a deadlock situation. If there is a cycle, means what? We have a deadlock situation. This is in the case where RAG has resources of single instance. Okay? Now, in situations where RAG has resources of multiple instances, at least one of them, then if you find the cycle in RAG, if you find the cycle, then we can say there is a possibility of a deadlock. There is a possibility of a deadlock. But we can't say we have a deadlock. Okay? When we say there is a possibility of a deadlock, basically this isn't safe. This statement is not safe. So what we can do, we can conduct additional investigation to know whether we really have a deadlock situation or no. Okay? Now we will show you what we can do looking at these 3 RAG examples. So the very first one, do we have a cycle? The first one to the left. Do we have a cycle here? Do we have? So do we have a deadlock? No. So the system is safe, right? Now if we look at the other one, do we have a cycle? So what's the cycle? Okay, P1, R1, P2, R3, P3, R2, back to P1. So this is a cycle. Do you have any other cycle? So when we have a cycle, now this is RAG and we have a cycle. And the resources are not of single instance. So it might be, right? Possibility of a deadlock. So now we can conduct additional what? Investigation. Now the node that has multiple instances is R2, which is involved in this cycle. This is not involved, so we can ignore this one, right? Now R2 has 2 instances, okay? One of them is in our cycle, which is this instant. Now let's look at the other one, the other instant. If it is also involved in another cycle, then we say we have a deadlock. We have a deadlock, okay? So in this case, we can see that the other instance is actually involved in another cycle, which is R2, P2, R3, P3, R2. So we have a cycle. So in this case, we say we have a deadlock situation. Now looking at the third one, do you have a cycle? We have a cycle, and the cycle is basically R2, P1, R1, P3, R2, right? So R2, P1, R1, P3, R2. This is a cycle. However, I have multiple instances here. Now let's see the instance, for example, here for R1. Is it involved in a cycle? Then it's enough for you now to say that you don't have a deadlock situation. Now let's prove that. Well, this R1, this instance of R1 is currently allocated to B2. B2 is not involved in a deadlock situation, right? Which means B2 will finish, right? With time, it will finish. And when it's finished, what is it going to do? It's going to release this resource, right? And if it is releasing this instance of R1, then P1 requesting an instance can be granted, which means this R will be changed to allocation, right? And in that case, I don't have a cycle in the very near future. Deadlock means forever you have the cycle, okay? So we're done here. Yeah, and we know why, right? We have to explain why. Now we said we can handle or look at deadlock in using three different methods. One of them is prevention, the other is avoidance. These are the two methods. There is a third one, as we mentioned, which is basically detection and recovery, right? In prevention, we want to prevent deadlock from happening. So here we are handling the problem from the root of it. Okay. For a deadlock to happen, 4 conditions must hold simultaneously, right? So if we can guarantee that any one of them will never happen, it means we will never have deadlock. That's how prevention. That's how prevention is. So we're going to look at these 4 conditions, and we try to see if we can make any one of the conditions false, or how can we make these conditions false, okay? The other one is deadlock avoidance. Deadlock avoidance, to use this method, we need additional information from the processes. Additional information. The information, in fact, is related to processes claiming all the resource types and the number of instances of these resources that are needed by the process prior to the execution of the process, okay? So the OS needs to know each process, what are the resources that it needs, and what are the number of instances of each resource. Need to know, okay? Knowing so, then the process for the OS, for each request of a resource by a process, the OS is going to perform an algorithm. That algorithm ensures that allocating the resources requested by the process will leave the system in a safe state. If not, then these resources will not be allocated. Okay? The process has to wait. We're going to talk about that in details and how can we do it in some like numerical examples and so on. Deadlock detection and recovery. Basically, we will just leave the system to have deadlock. Okay, so we are not doing any checking. However, from time to time, we're going to run a test. We're going to run a test to see whether we have deadlock situations happening in the system here or there. And if we found that there is a deadlock situation, then we have to follow a particular algorithm, okay, or a particular strategy to what? To recover from deadlock. Here the assumption is that deadlock is not frequently happening, rarely happens, okay? So you don't have to continuously, performing an algorithm as what we're doing in deadlock avoidance for each request, because that's a delay, right? Each time a process requesting a resource, then you have to execute a particular process. That's delaying. Okay? So if it's rarely happens, deadlock, then we will choose the last one. In fact, most of the operating systems, they choose the last one. Now let's look at the deadlock prevention. Look at the conditions and we try to make them false, okay? So if you want to make the very first one false, in fact, it won't work with us, so we're gonna just leave it. The reason is that some resources in the system are by default shareable resources. For example, read-only files, there are shareable resources. So many processes, they can access them at the same time. And that's no problem. But however, some resources in the system, they are strictly, what? Strictly accessed by one resource at a time. For example, printer. Okay, printer is a resource. To print, we can't just have two processes printing simultaneously to a printer. Okay? Send a little bit of data of the file that you want to print by process A, and then process B send a little bit of the data that has to be printed, so that at the end, the printing result will be a mess, right? Mixing between the data of the two processes, okay? What's happening is we have a shared printer, or the sharing is different than what we're seeing in here. Basically, the sharing there, you send your job, and then another one sends the job. There will be queuing waiting, so but you send the full job, right? So we're going to leave the first condition. We have another 3 conditions to work with. Now, the second condition to work with, it is basically hold and wait condition. It says that we have a process, okay, holding resources and waiting for additional resources. Additional resources that are held by another process. We can make this not to happen by deploying any one of these 2 protocols, any one of them. The first one says the process must gain all of its resources, must have them allocated prior to its execution. So it will never ask for an additional resources, right? It will not wait because it has all at once. At the beginning, it has none. Request all, have them all, and use them, okay, until finished. This one protocol, okay. Another protocol says that a process will be requesting resources. Fine. But now we have to be careful. We should not request additional while holding some. So a process requests resources because at the beginning it has none. These resources, once they are available, they are allocated to the process. So now the process has some resources. If it needs additional resources, then it should release what it has first, and then request the additional resources. So if a process having currently resource A and would like to have resource B, what should it do? Release A and then request B. Now what if it needs A and B together, okay, later on, but it found that it has A, however it needs B? Then it should release A, request A and B, right? Now this will make the execution of processes a little bit difficult, but we avoid deadlock. In systems where deadlock happen very frequent and it's critical to handle them, then you can use something like this, okay? An example of that, like if you want to get data from a file, okay, and then you want to sort this data, and then you want to print them. So basically you need what? The drive, okay, for on which the file is saved. So that's the resource that the process is supposed to get. So here we're taking from a tape drive, and then we are doing a sorting, and basically we're going to copy it to the disk, okay, and then do the sorting, and then after that send it to the printer. So 3 resources are needed, okay? So getting them one by one is a problem. Now if these resources are common resources, we call them like expensive resources because they are commonly requested by other processes, then it's very difficult to what? To get them, okay? So as a result, we might have some kind of starvation, okay? And if we are like using the very first protocol, a process must gain all of its resources at the very beginning. So a process needs resource A, B, C, D, and E, while in fact, so gonna get them all at the very beginning, right? Based on the first protocol. Resources from A to E. Now, if it only needs E towards the end of it, the end of the execution of the process, it means that this process had been holding resource A, E, for all of that time, while actually it needs it towards the end. So blocked other processes from using this resource. So here we say that what? We have low utilization of resources based on that. The other way is to look at the condition of no preemption. No preemption. We said that the process voluntarily, what? Preempt the resource that it is holding. But we can make it not. It means we can force the process to what? Preempt the resources that it has. We can follow either one of two protocols to adopt or to deploy. One of them is that when a process holding some resources and requesting for additional resources, then if the requested resources are not currently available, what are we going to do? We're going to release all the resources that the process is having. So you request, either you gain or you lose. Right? Either gain or lose. So a process, if requesting resources, and the resources are available, will gain them. But if requesting resources, and the resources are not available, then we'll lose even the ones that it has. Okay? So this is one protocol. And for that, for it to restart later on, it has to gain the resources that it lost and the ones that it requested earlier. In another protocol, okay, if a process is requesting resources, currently holding some and requesting additional ones, then if these resources are not, if they are available, then the process will proceed. No problem with that, right? But if the resources are not available, then we do one additional checking. Because it could be that these resources not available because held by another process which is not active, is waiting. So in that case, what do? We preempt these resources from the waiting process and we allocate it to the process who's requesting it. Okay? If not, then the process has to wait. If these resources are with an active process, not a waiting process, then basically you cannot allocate it, and in this case, what? Have to wait. And by that, it will be losing the resources that it was holding as well. Now, these implementations, we can do it for what resources that can be easily stored in terms of their state. Okay, we can restore their state, such as CPU registers, memory spaces, and so on. Now, the last one is circular wait. How can we prevent that circle from happening? Okay, the way to do it is by deploying this way of assigning resources to processes. At the very beginning, we're going to enumerate processes. We're going to give an integer number, okay, for each resource. So all resources, they have what? Numbers. They are certain IDs. Now, we're going to use this rule. Process will request resources in an increasing order of their number, their ID, okay? Which means, if a process has a resource, currently holding a resource of, say, ID 3, then no problem for it to request a resource of ID 9, or ID 10, or 4, right? But if a process holding a resource of ID 3, then it cannot request a resource of ID 3 even, 2, 1, right? Or if we started the enumeration of 0 as well, right? So you request resources in an increasing order compared to the one that you're already holding as a process. Now this guarantees that we will never have what? A circular wait. Can you explain why? What is circular wait? P0, holding resources, requesting for ones that are held by P1. Let's start by the cycle this way. B0 holding resources, requesting others that are held by P1. Now these resources requested by B0 and held by B1, their ID should be greater than the ones B0 having, right? Because we're having this rule, correct? Do we agree on this? B0, if it's currently requesting resources of P1, okay, this means that the requested resources are of higher ID than what B0 having, right? Okay, now let's continue. P1 requesting resources from P2 means the resources IDs held by B2, which are requested by B1, are greater than the ones in P1. Now let's take a cycle of 3 processes, okay? Now P2 requesting resources that are held by B0, okay? This means that the ID of these resources held by B0 are greater than the ones held by P2, correct? Doesn't that contradict with our early assumption that the resources of B0 are less than, in terms of ID, the resources held by P1? So we prove that by what? By contradiction, okay, can easily be proved. So in fact, if we deploy this rule, okay, then we will never have a circular weight. Now the other way of dealing with deadlock, today we'll just show you the type of data kept by the operating system. If we have time, we'll show you an example as well. Dealing with deadlock using avoidance. We said for us to use this, then we need additional data from the processes. Basically, the data that is needed from the processes, the type and number of resources needed by each process before it starts. Okay? We are not going to allocate it, but we need to know it. Okay? For each process, what type of resources it needs, and how many instances of each resource on maximum for each one of the processes. Okay? And then for each request, later on when the processes they start, for each request by a process, we're going to execute an algorithm. This algorithm will check. Granting this request will keep the system in safe state. If yes, the resources are granted and they are assigned to the process. If not, then the process has to wait. Now, let's do that in terms of numbers. Okay? But first, since I already been mentioning safe state, okay? What is a safe state? A safe state is the property that we can execute the active processes in the system, okay, in any order that we want with the currently available resources. Execute them all, okay? Which means if you give a number of processes and then you're given certain set of resources that are currently available, okay? And if you manage to execute them all, means give each process, okay, what it needs to finish in terms of resources, then you manage to find what we call an execution sequence, okay? An execution sequence, an order in which you can execute all processes who are requesting resources in the system. If you can do so, then we say this is an execution sequence guaranteeing that the system in safe state. System in safe state. But if we can't find so, then the system is not in safe state. Safe means we don't have deadlock. Unsafe means there is a possibility of having deadlock. Okay? We can't say we have a deadlock, but there is a big possibility that there is at least a possibility that we have what? Deadlock. Now for single instant resources, we said we can use the RAG. Okay? So for each request, we will check. If that's going to cause a cycle, means better not to have it. Okay, better not to grant this request, because that will lead us to what? A deadlock. A deadlock immediately, right? If not, then it's fine to have it, right? On the other hand, if we have multiple instances of the same resource, then we can use an algorithm which is called the banker's algorithm. Banker's algorithm. For the resource allocation graph, as I mentioned before, we have claim edges, we have assignment edges, okay? We have claim edges, request edges, and assignment edges. And this basically from to process and resource. So if I have something like this, okay, this is an initial state of 2 resources and 2 processes, okay? I don't have any cycle in here. I have a request, okay, and I have an assignment, and I have 2 claim edges. 2 claim edges. So I don't have a cycle at all. However, if I have this, then I have a possibility of what? Deadlock. Because if process P1 here decided to request R2, then what would I have? A deadlock. I have what? I have already a cycle, and that is a deadlock. Now, the general one, which is basically the banker's algorithm, can work for all. Single and even what? Multiple instances. What we need to do is to have prior information about each process. In fact, the kind of information that is supplied is what we call max. Okay? Max. Number of processes and the type, the number of instances of each type available in the system. Initially, the system has certain type of resources. So it might have resource type A, B, C, D. Okay, regardless of what is A, B, C, D are. And it might have 5 of A, 5 instances of A, 2 instances of B, 1 instance of C, let us say, and maybe another 2 instances of D. So types and instances. That's what the system has overall. Okay? Then we would have the processes executing in this system, and they would need what? Resources. Here, we want each process from the very beginning, okay, to inform the system with information related to the type of resources and instances of these resources needed by this process to finish, okay, on maximum. That's why it is in the max array. The max array is m by n, n by m, having n processes, and m resource types. So I will have a row entry in this matrix representing the number of instances of each resource type by a particular process. So I say max ij equals k, for example, max 23 equals 4. What does this mean? Max 23 equals 4. It means process 2 will need on maximum 4 instances of resource 3, which I read it here. Process I will need on maximum k instances of resource type J. Okay? We will see that in a while. Available, as we mentioned, the resources that are available in the system, number of instances of each resource. Allocation, initially is 0. No resources allocated to any process. But with time, processes will be allocated resources, and we need to keep track of these resources. Needed is what is left for a process to request. So needed is, in fact, it is the matrix max minus allocation. Max minus allocation. What the process claimed as a maximum use of resources minus what it currently has will give us what it is left with or need in the future. Okay? So an example of that, I think numbers make things much clearer. Okay? If we have a system with 3 types of resources, A, B, C, where we have 10 instances of A, 5 of B, and 7 of C. That's all the resources the system has. Okay? And if we have processes P0 to P4, 5 processes active in the system. At the very beginning, P0, okay, claim that it will need on maximum 7 instances of A, 5 of B, 3 of C. Okay? And P1 up to P4 also they claim their needs of these resources. For example, here P2 claim that it will never need resource B, which means it should never request it. Okay? And it will never need more than 2 resources of C. Means should never, okay, what? Request more than 2 that this is including the ones that it has. Okay? So this is max. And this is available, which I will explain in a while. Now, we looked at the system at one point of time. We found that, of course, this max doesn't change. Max doesn't change, okay? We found that currently P0 is using 1 resource of A. So this is how I read allocation. Okay? Currently, P3 is using 2 resources of A, 1 resource of B, 1 resource of C. Currently, P4 is using 2 resources of C, but none of A and B. Okay? Now, it's fine for P4 to request another additional resource of C, but not more than 1. Okay? It can request up to 4 resources of A, 3 resources of B. Because in total, okay, the request plus the allocation should not exceed what? Max. Okay? Now, the needed. Needed is what the process will need. Looking at what it claimed earlier and what it currently has. So this is a process that claims 7 of A, 5 of B, 3 of C. Currently is using 1 of B. Means it might need 7 of A, 4 of B, and 3 of C in the future. So this is the needed, the leftover of what it can claim. Which means any request by B0, which is a composite request, it might be a request of certain number of resources of A, others of B, others of C. This request of B0, I should always compare it to what? Needed. It should not be greater than needed, right? A process cannot request more than what's needed, because needed is the difference between maximum and allocation, right? Now, available. Available is the leftover number of instances of each resource type. Initially, we have 10 of A, 5 of B, 7 of C. That's all of what the system has. But currently, we have certain allocations of them. Now, if you see A, how many allocated? 7. 7 instances of A currently allocated. 2 of them for P1, 3 for P2, and 2 for P3. In total, we have 7 resources of A allocated. But we have 10 initially. 7 allocated, we are left with 3 available, right? So that's how we calculate available. So available can be calculated from what? From the allocation. Now, we say a system is in safe state if we can find an execution sequence. An execution sequence means we will look at the processes and their needs. Right? We are trying to finish the process, to make it finish. For a process to finish, then we will see. If we can give it all what it needs, then it can finish. So here, For example, if I look at this, P0, let's try to find an execution sequence. P0, can I give it what it needs to finish? What it needs to finish are 7 of A, 4 of B, 3 of C, and I don't have it. So I cannot finish B0, okay? But that doesn't mean there isn't an execution sequence. I can try to finish another one, and then get back to B0. Because when I finish one process, what does it mean? Claim back the resources that it was using, right? So for example, here P1, it needs one resource of A, 2 of B, and 2 of C, and we already have them in the system, which means it can finish, right? If I give it, because I can give it what it needs, so it will finish. And if it finish, then I will claim back what it has. Means after P1 finished, I will have an additional 2 resources of A added to what I have here in A. So I will have here 5, 3, 2, okay? So this is how we do that, okay? We loop through the processes. This is an algorithmic representation of how we found an execution sequence, okay? You can put them in an array, okay, their needs, and then try to execute them, always looking at what available, okay? Now, let's do that for the state that you have just seen. So if we try to execute P1, we can't, because it needs more than what's available. However, if we try to execute P1, P1 needs what? 1, 2, 2, which I have, right? So I will execute it. Assuming that it has finished, then I will claim back what it used to have, which is 2. So I will have 5, 3, 2 after P1 is finished, right? Now let me try to execute P2. P2, it needs 6 of A, which I don't have, because currently I have 5. So I will skip P2 for the time being and try to execute P3. P3, it needs 1 of B, 1 of C, which I have, because now I'm here, right? So I will execute P3. Executing P3 means I will gain all the resources that is currently holding after finish. 2, 1, 1 will be added to 5, 3, 2. The result is 7, 4, 3 after executing P3. Now I'll try to execute P4. P4 needs 4, 3, 1. And I already have more than that, which means that I can execute it and it will finish. And by that, I will claim the resources that it used to have, which are 2 resources of type C. That I will add them here to these, so I have 5. So now I have already executed P1, P3, P4, and I have 7 resources of A, 4 resources of B, and 4 resources of B and 5 resources of C, right? Which means I can execute P0, can I? And I can execute P2 as well, right? So if I am to execute P2, okay, then I will claim of what P2 used to have. B2 have 3 and 2 is 302. 302, I will add them to B2, to what I have in here in available, assuming executing B2. Now I'll try to execute P0. P0 needs 743. I have more than that. And I will assume that it's finished, so I'll claim back what it has as P0, which is 1 resource of B. I will add it here. So I managed to execute them all, P1, 3, 4, 2, 0, okay? You can find execution sequences, not one sequence, multiple sequences as well, okay? But as a result, what do we have? We have the system claiming back all the resources that it initially has. So we have an execution sequence. Our conclusion, the system is in safe state. Next, we will talk about how to handle requests by processes, whether to grant them or to make the process wait, or maybe sometimes to terminate a process because it's violating the request rules. Okay, next time we'll talk about that.